Welcome students. Let us see topic 8.3 Universal Law of Gravitation. It is believed that Newton saw an apple falling from a tree, which inspired him to give the universal law of gravitation, and from that only he explained gravitation between all the terrestrial bodies. But that is not the fact at all. Basically, Newton came to the conclusion of universal law of gravitation by finding the centripetal acceleration of moon due to Earth's gravity. How it is so? Let me explain you by this figure. Here you can see this is Earth and here is the orbit of moon. Here is moon and moon is having a velocity v in the tangential direction. The radius of the orbit of moon is Rm and radius of Earth is Re. Alright. Now, because moon is revolving around Earth in a circular path, so it must have some centripetal force. Now that centripetal force would be due to the gravitational force of Earth on moon, and due to this centripetal force there would be a centripetal acceleration which I am naming as Am. It is centripetal acceleration on moon, so I am writing Am for it. Now the equation of this centripetal acceleration Am can be written as v square upon radius, that is Rm, right? Now if the periodic time of moon when it is revolving around Earth is, let us say, t, then we can write that this speed v will be 2 pi Rm upon t. I am using the definition of speed only. Speed is equal to distance upon time. So v is equal to 2 pi Rm upon t. So that I can place here at the place of v square. So v square will be 4 pi square Rm square. But here in denominator 1 Rm is there. So 1 Rm will be cancelled out. Remaining is 1 upon t. Here we already know the value of Rm. Rm is the radius of orbit of moon and that is 3.84 into 10 raised to 8 meter. As well as we know the periodic time of moon around Earth, that is 27.3 days, right? This I have to convert into second. So it is 27.3 multiplied by 24 multiplied by 3600. That gives us 2358720 second. This is the periodic time. Now we can place this value of Rm and t in this equation. So we will get the value of centripetal acceleration of moon, that is Am is equal to 0.00272 meter per second square. Now you can see here that the value of this acceleration is very less compared to the gravitational acceleration on the Earth's surface, that is g is equal to 9.8. Means here at a distance Rm the gravitational acceleration is just 0.00272 and on the Earth's surface it is 9.8. So this difference suggests that as you move away from the Earth's surface, the gravitational force is rapidly decreasing, and that's why the gravitational acceleration is also rapidly decreasing. Newton assumed that the gravitational force would be inversely proportional to the distance square, and that's why the acceleration would be also inversely proportional to the distance square. That means Newton assumed that the acceleration due to gravitational force, that is A, is inversely proportional to 1 upon r square, where r is the distance of the object from the center of Earth, right? Now as per this equation we can write here that the acceleration of moon at a distance rm is inversely proportional to rm square, and the gravitational acceleration on the Earth's surface is inversely proportional to the radius of Earth re square, right? Now we can take ratio of both of these equations, and so we can write that am upon g is equal to re square upon rm square, or we can also write like am is equal to re upon rm whole square multiplied by gravitational acceleration g. Now we know all of these values. Radius of Earth, that is re, is 6.4 into 10 raised to 6 meter. Rm is already there, 3.84 into 10 raised to 8 whole square, and then multiplying with g, where g is 9.8 on the Earth's surface. Now solving this, we will again get 0.00272 meter per second square. This is centripetal acceleration on moon am. Now note here that we are getting the same value of am again. Previously we got this value of am by the equation of centripetal acceleration, and now we are getting the same value of am by the assumption given by Newton that gravitational force is inversely proportional to the distance square, and both of these values are coming same. That means Newton's that assumption that gravitational force is inversely proportional to the distance square is correct. Now these observations led Newton to propose the universal law of gravitation as below. Let us say that these are two mass particles, like having mass m1 and m2, and the distance between them is, let us say, r. So here Newton said that both of these particles will attract each other by gravitational force F. Obviously this force will be same in magnitude and opposite in direction. Not only that, this force would be proportional to the product of both of the mass. That means F is proportional to m1 m2, and this force would be inversely proportional to the square of the distance between both of the mass. That means F is proportional to 1 upon r square. So from this we can write that F is proportional to m1 m2 upon r square, right? Now let us see the statement given by Newton for universal law of gravitation. It is like this: every body in the universe attracts each other with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. That means, as I said already, F is proportional to m1 m2 upon r square. Now here we can put a proportionality constant, and then equation will become F is equal to g m1 m2 upon r square. Here this g is known as universal gravitational constant. It's a constant named as universal gravitational constant. Now this was the equation of gravitational force in scalar form. Now let us see the same in vector form. Now here is the xyz coordinate system, and let me show a particle here. This is the first particle having mass, let us say m1, and this is the second particle having mass, let us say m2. Let me show the position vectors as well of both of these particles. Here are the position vectors. Let me name them as r1 and r2 vector. And finally, this is a vector between both of the particles 1 and 2, and let me name it like vector r. Then you can see here that this is making triangle of 3 vectors, and here you can see that this is first vector, this is second vector, and this becomes the resultant vector. That means we can write here that vector r2 is vector r1 plus vector r, or you can also write that vector r is equal to vector r2 minus vector r1. We can also name it like vector r21. Mind well, I am giving a new name vector r21. How I am giving this new name vector r21? It is because that this vector is a position vector of point 2 with respect to point 1. So we should name it like vector r21, position vector of 2 with respect to 1, that is r21. Now using this information, first I will find force on particle having mass m2 due to the particle having mass m1. In short, mass on 2 due to 1. So obviously we can name it like vector F21. This is force on 2 due to 1. Now the equation can be written as G m2 m1 upon the distance square, that means r square, and here I should mention minus caret r. Look this, the force on particle 2 due to 1 will be towards 2 to 1. Let me show, this is force F21, right? It is from 2 to 1. Obviously that is opposite to the vector r. So it is also opposite to the unit vector caret r. Caret r will be from 1 to 2 and the force F21 is from 2 to 1. That's why I have to introduce here a minus sign. We can also write this equation in this way. Vector F21 is minus G m2 m1 upon r21 square, and here caret r21. Look, this changes. As I have shown in the above equation here, that vector r is equal to vector r21. So at the place of r I am writing the magnitude r21, and at the place of caret r I am writing caret r21. You should remember this equation, that is in vector form. Now from the same we can write the equation of force on m1 due to m2, force on first due to the second particle. This can be now written as F12 vector, and that will be equal to minus G here m1 m2 upon, this should be r12 square and caret r12. Okay. Now I can also write this equation as minus G m2 m1 upon r21 square, and here minus caret r21. Now see what changes I have done. See, instead of m1 m2, obviously you can write m2 m1 as well, and magnitude of r12 or magnitude of r21 both will be same. This is only magnitude. So they both will be same because it is basically distance between 1 and 2. Either you measure from 1 or either you measure from 2, the distance R12 and R21 will be same. The important change is here. At the place of caret R12, I have written minus caret R21 because they both will be in opposite direction. Right? Now, here there are two minus signs. But if you consider only one minus sign, then this equation is nothing but the equation of F21, vector F21. See this equation of vector F21. It is minus G M2 M1 upon R21 square and caret R21. So, at the place of this term, I can write minus F21 vector. Means vector F12 is equal to minus of vector F21. That means here Newton's third law is also obeyed. So in case of gravitational force, Newton's third law is also obeyed. Now let me tell you one note here, that sometimes you will find this equation in a very different manner. See, we know that caret R21 can be written as vector R21 upon magnitude of R21. This is nothing but unit vector is equal to vector itself upon its magnitude, right? And so at the place of this caret R21, I can put vector R21 upon R21. But here already R21 square is there in denominator and you are adding one more R21. So what will be the equation? In this case, the equation of F21 vector can be written as minus G M2 M1 upon R21 cube, and here vector R21. This will be now vector R21, not unit vector R21, right? So here you will get a vector R21 and here you will get a cube of magnitude R21. Now let us see what happens if one particle feels force due to other two or more than two particles. This is known as superposition of gravitational force. Let me explain you. Suppose here is a particle having mass m1 and here is another particle having mass m2. Here is another particle having mass m3 and one more particle is here that is having mass m4. Now all of this particle will apply force on this particle m1. Let me show all of these forces. This is force on m1 due to m2, then this is force on m1 due to m3 and this is force on m1 due to m4. Now let me show the direction of all of these forces and then after I will name them. See, the first force is force on 1 due to 2. So I should write it like F12, vector F12. The second force is force on 1 due to 3. So I should write vector F13. And the last one is force on 1 due to 4. So I should write vector F14. So now we can find out the resultant force on particle M1. Resultant force on M1 is, we can write it like F1 only, and this F1 will be equal to vector F12 plus vector F13 plus vector F14, right? Now when I will put the equation of all of these forces, I will get minus G as common and then the remaining term from F12 will be M1 M2 upon R12 square and here caret R12. plus the next term will be of force F13. So it will be M1 M3 upon R13 square and caret R13. And finally the last term is of force F14. So that will be M1 M4 upon R14 square and here caret R14. So this is the total equation of force on particle M1 due to M2, M3 and M4. This is also known as superposition principle of gravitational force. Alright. Now let us see gravitational force between an extended object and a point mass. Listen, up to now we have seen gravitational force between only point-like mass. But now here we'll take one extended object and another point-like mass and we'll check what is the gravitational force between them. Here we'll take two cases. This is the first case. Let me show the figure also. Here is the figure. You can see this is a spherical shell, hollow spherical shell, alright, having mass capital M, and this is a particle of mass small m. The distance between both of the centers is r. This is the distance from the center of this hollow sphere and to the particle, that is r. So now the question is that what will be the force on this particle of small m mass? Here is the statement. The force of attraction between a hollow spherical shell of uniform density and a point mass situated outside is just as if the entire mass of the shell is concentrated at the center of the shell. See, this is a shell of mass capital M and you are placing a particle outside. Then in such case, the shell behaves such a way that the whole mass of the shell is concentrated at the center of the shell. Means here the center of the shell behaves as if it is having the total mass capital M of the shell. That means this point O behaves as a particle having mass capital M. Now this is another particle and the distance is r between them. So obviously the force on the particle will be equal to just G small m capital M upon r square. You can see this is nothing but the equation of force between two particles having mass small m and capital M, which is applied here for a shell and a particle. Alright. Now let me explain why this is happening so. See, this shell can be considered as if it is made out of many tiny particles, right? All of these tiny particles will be having some mass, and due to their mass, all of this particle will apply gravitational force on this particle of small m mass, and that all forces will be somewhat like this, right? Here, for all of these forces, you will get two components. One component will be towards the center of this shell and another component will be perpendicular. But all the perpendicular component in the upper half and the lower half will be cancelled out. So obviously all the components towards the center O will be just added. That means the total force will be just towards the center O on the particle of small m mass. Not only that, this force can be calculated and it will be just equal to F is equal to G mm upon r square. Now let us see the second case. Here is the second case. Let me show the figure for this. Here it is. Here you can see the particle of mass small m is situated at the very center of the shell of mass capital M. This is shell and this is the particle at the center of the shell. Now what will happen in this condition? Here is the statement. The force of attraction due to a hollow spherical shell of uniform density on a point mass situated inside it is 0. That means the force on this particle will be just 0. Let me write here that the force on the particle will be just 0. Not only that, if the particle of mass small m is kept somewhere away from the center, see, this is the shell and this is the center, but the particle of mass small m is kept away from the center, then in this condition also the total force on the particle is 0 only. Now let me explain that why in both of this figure total force becomes 0. See, again here also this shell can be considered as if it is made out of many small particles. Alright. Now all of these small particles will be having some mass and they all will be applying force on this particle of mass small m. So there will be many forces on this particle small m in all the directions of same magnitude, and that's why the resultant force will become just 0. Now if we discuss about this second figure, then here the particle of mass small m is not kept at the center but it is away from the center. But still what will happen here? See, all the tiny particles of this shell in this right side will be having small distance. That's why the force on this particle due to the tiny particles here will be very strong. Alright. Whereas on the left side, if we discuss, all the tiny particles of the shell on the left side will have large distance from the particle m. Right. So their force will be rather weaker. Okay. But the number of forces in the left side will be more, whereas the number of forces in the right side will be less. So what is happening? In the left side, the number of forces are more, but the forces are weak. In the right side, number of forces are less, but all the forces are very strong. So as a result, the total force again on this particle small m becomes 0. So here also the total force is remaining 0. This means that if we place any particle inside a shell, a spherical shell, at any place, either you put on the center or here somewhere, or even if you put the particle which is touching the inside surface of the shell, then also the total force on that particle will be always 0. Alright. So with this, I finish my lecture here today, and you will get all the question answers of the topics taught today in a PDF form in the description below. Alright. So herewith Anshul Baldania is signing off. Take care.